In this video, I want to talk about the VSEPR model with 4 electron pairs, or 4 electron groups, which gives us tetrahedral geometry. So tetra, the prefix means 4. We're talking about 4 electron pairs when we're talking about the valence shell electron pair repulsion model, which gives us information about the geometry of a molecule, not just the way that all these electron groups are arranged around a central atom, but also how the atoms are. And there's kind of a distinction there between the geometry of the electron pairs, which we call the VSEPR geometry, and the molecular geometry, which is what the shape of the actual molecule is. So for the VSEPR model, when we say electron pair, it's also called electron groups. And what we mean by that is either a covalently bonded atom. So I like to use the terminology number of bonded atoms. And then we could also use it to talk about a lone pair or a non-bonding pair of electrons. So when I'm making the distinction between the two, all of these count as electron pairs for the total number. But I like to make the distinction between bonded atoms and lone pairs. And I use bonded atoms instead of covalent bonds because the covalent bond can be single, double, or triple. So then you don't have to think about, well, how many electrons are there? It's really just about how many bonded atoms there are. Okay, so for 4 electron pairs, we have tetrahedral geometry overall, and there's really 3 options. And this is going to be true with all of the VSEPR model geometries, is the number of electron pairs that you will have that many n-1 options for shapes within that geometry. So if I have 4 electron pairs, n-1 there gives me 3 different options for molecular geometries, or the shape of the molecule. So for 4 bonded atoms, then I have a structure that looks like methane here. We'll use methane as an example. And I have kind of my tetrahedral model here as my mascot for this video. So if I look at carbon and 4 hydrogens here, my methane, the total number of valence electrons I have to work with is 8. So you always start off to figure out the geometry of these things by doing the Lewis dot structure. So if I look at the Lewis dot structure of methane, then I've used up 2, 4, 6, 8 just by making the skeleton, so I've already used up all my electrons. And this is okay because my carbon is full, it has a full valence, and each of my hydrogens has a full valence as well because they're happy with 2 electrons in that 1s orbital, which is where their 1 electron each is hanging out. So if it has 2, it has a full valence. That satisfies the octet rule even though it's not an octet. So here's our methane. So if we're looking at this and trying to analyze what the geometry is going to be, I'd say, well, carbon is my central atom. So around that carbon, I have 1, 2, 3, 4 bonded atoms. And if I look at carbon, it has no lone pairs. So when I'm categorizing it here, I'm saying 4 bonded atoms. That's what I mean by this. 4 atoms, 0 lone pairs. When I add them together, I end up with 4 electron pairs total. So I know that my VSEPR geometry, sorry, I'm a mess. Valence shell electron pair repulsion. It's the problem with saying VSEPR all the time, then I want to actually spell it some way differently apparently. So valence shell electron pair repulsion geometry. So it has tetrahedral geometry, which is this guy. So a tetrahedron is a 4-sided pyramid, and so I'm going to draw it like a tetrahedron. And if you've seen my past videos on VSEPR, you'll know that we have a specific convention for drawing this 3-dimensional structure on a 2-dimensional surface. And that convention is that we have straight lines, just a normal line, which indicates that they're in the same plane as each other. So I'm going to use this kind of orientation when I'm drawing it, where my central atom and these 2 outer atoms are in the same plane. That's what I've represented here. And if I'm looking at my molecule, then this one's kind of coming out at you, and the other one is going back into the page. So we're going to represent this one coming out at you with this blocky triangle, and this one going back into the page that I'm drawing on, into the surface that I'm drawing on, with this kind of triangle that's getting smaller with hash marks. Okay, so there's my tetrahedron. My angles on this thing, They're all the same. They're 109.5 degrees. And because we're talking about geometry, sometimes it's kind of hard to see kind of how this and this are related to each other. So as you're drawing these and practicing to start off with, I kind of like to draw in the lines here. So if I connect the lines of my base and I connect the lines of my legs here, now I have kind of this four-sided pyramid, my tetrahedron shape, that mimics this sort of ball and stick model, which represents the same thing. So 109.5 degrees is the magic number for our tetrahedron. So the VSEPR geometry is tetrahedral. I drew it like a tetrahedron. Now what the heck is the molecular geometry? Remember, molecular geometry is the shape of the molecule. And this is going to be the case for all of the different geometries. If you have the same number of bonded atoms as you do electron pairs, so the same number of atoms as electron pairs, then the molecular geometry is the VSEPR geometry. And I like to make the distinction between the two is that the shape is the tetrahedron, but it has tetrahedral geometry. So my shape is a tetrahedron, but it comes from the tetrahedral geometry from having 4 electron pairs, regardless of whether those pairs are bonded atoms or lone pairs, which in this case, they're all bonded atoms. Okay, that's option 1. That's, again, the easiest is when all the atoms are the electron pairs because your molecular geometry is your VSEPR geometry. So let's look at the next option where you have fewer numbers. If we have 3 bonded atoms, then we have a structure that looks like ammonia. So if I'm thinking about ammonia, nitrogen has 5 valence electrons, hydrogen has 1 each, so I have 8 electrons total to work with in my structure. To figure out my geometry, I need to draw my Lewis dot structure first. So I'm going to draw my skeleton first. I've used up 246 of my electrons that I have to work with. That gives me 2 left over. My hydrogens are all happy, so normally I would put them on the outer atoms first, but because they're already full, because they're hydrogen, I'm going to put that leftover pair on my central atom, and that uses up all 8 of my electrons. So I'm going to highlight my lone pair here with kind of a bubble, which I just think shows that there's some space that is taken up by this lone pair. So now we're going to do some accounting to figure out what the geometry is of this. So we have 3 bonded atoms. And in this case, because nitrogen is our central atom, so 1, 2, 3, we have 1 lone pair. So when we add those together, we end up with 4 electron pairs, which gives us tetrahedral geometry. So the VSEPR geometry of this structure is tetrahedral, so I can draw it like a tetrahedron. So I'm going to draw it like a tetrahedron, where my lone pair here and my hydrogen are in the same plane, right? So these guys are in the plane of the surface. Then one of the hydrogens is coming out at you. This is always going to be the schematic for your tetrahedron, and one of them is going back into the page. So essentially I have a tetrahedron, but I've taken the top off. So I end up with a structure that doesn't look like this because this has 4 atoms on it, but it looks like this guy. So this is my ammonia, where I have a lone pair here kind of coming off the top. Now our predicted angles for ammonia would be 109.5 degrees because it has tetrahedral geometry. But because this lone pair takes up more space, so the lone pair takes up more space, than an atom would. So if I had an atom there, everything would be 109.5 degrees. But now I have this bigger thing here that's going to compress down these angles. So the angles in my ammonia here are actually 107 degrees, slightly smaller than that predicted 109.5. And again, that's because this lone pair is taking up slightly more volume in the molecule than an atom would. Now, if I think about my shape then, because that's kind of the name of the game here, the shape of this thing is no longer a tetrahedron because I don't have the 4-sided pyramid. I don't have 4 atoms anymore. I only have 3. So my molecular geometry, or my shape, we'll go molecular geo here, is trigonal because of the 3 atoms. or triangular. You'll see it both ways, trigonal or triangular. And then it's still got a pyramid shape. So this is trigonal pyramid geometry, or trigonal pyramid shape. So it's no longer a tetrahedron, but it has tetrahedral geometry. Again, it's kind of a tricky thing about VSEPR because we have this overall geometry that tells me where these different electron pairs are and how they arrange themselves around this central atom. But based on how many of those pairs are atoms is going to give me a different shape name. So if I have 3 bonded atoms and 1 lone pair, I have a trigonal pyramid. Compare this to the idea that if I have 3 atoms around a central atom, I could have trigonal planar geometry. So the difference between this guy, which is totally flat, and this guy, which has that kind of out of the plane look to it, is that lone pair. So that lone pair gives it tetrahedral geometry, 4 things around a central atom, so it brings it out of the plane. Okay, now let's go to the next option. So here's option number 3. If we have 2 bonded atoms, we have a structure that looks like water. So how many valence electrons are we working with here? So we have 6 electrons from my oxygen, 1 each for my hydrogens. That gives me 8 total. When I'm doing the Lewis dot structure of this thing, then I end up with oxygens and hydrogens. Here's my skeleton. I've used up 4 electrons in building this skeleton, so I have 4 electrons left over. The hydrogens are happy, so I'm not going to put them on the outer atoms. Instead, I'm going to put them on the central atom. 1, 2, 3, 4, which use up the rest of those guys. Now again, I'm going to highlight my electrons here with kind of bubbles to show you that there are 1, 2, 3, 4 things around this central atom. So my central atom is oxygen. I have 2 atoms here and 2 lone pairs. So that gives me 4 electron pairs total, which is tetrahedral geometry. So I have VSEPR geometry that's tetrahedral, so I can draw this thing like a tetrahedron, and I'm going to. So here's my oxygen. I'm going to draw my lone pair and one of my hydrogens in the plane of the paper in the same way that I did with my ammonia up here. Now, one of my other hydrogen is going to come out at you, coming out of the page, and then going back into the page is my other lone pair. So the 3-dimensional structure of this thing, I still have a tetrahedron. I would still predict that it's going to be close to 109.5 degree angles, as we saw with our ammonia up here that's going to change slightly with a lone pair versus an atom. So this gives me my tetrahedral geometry and a general sense of what this thing looks like. So I start here with my tetrahedron, and now 2 of them, 1, 2, are lone pairs. So now I just get this part of it, right, with these guys being lone pairs. So my shape is now this. Right, I started with the tetrahedron, and now I still have these lone pairs coming off, but we're not going to see them because they're electrons. They're teeny tiny. What we see when we're thinking about them, the whole molecule, are the atoms, and that's what we care about with the molecular shape. So the name of this guy, with my lone pairs here, here's my molecular geometry, is the highly scientific term bent. It's a bent molecular geometry. Sometimes you also see this as angular if you prefer kind of a more scientific sounding name. I like bent because I think it's hilarious. I think that chemists sometimes don't have a lot of creativity when it comes to naming things, which sort of cracks me up. So I just kind of like that. So we have a bent molecule because it's the 2 legs of my tetrahedral pyramid there. And so the molecule itself, all that we would see with these atoms, where the atomic nuclei are located, is in this angular kind of shape. Now, if we think about the angle, because we're thinking about geometries here, we have 2 things compressing down on this, right? 2 things that take up more space, so they're going to compress down on this angle even more. And the angle in a water molecule is something like 104.5 degrees. Sometimes you'll see this rounded as 105 degrees, depending on the text that you're using. Okay, so all of these molecules that we've seen have tetrahedral geometry, and these are your options.